assignment too for weekly? Weekly? How would that be?
What?
I said weekly assignment.
Oh, yeah.
Too.
Yeah, I'm not doing that.
No.
Okay, so exam 3 is on Friday. And the topics are everything up through the second law, which I guess in the problems is often called entropy. So that stuff. So there are no questions on the exam about the Rankine power cycle. Anybody have any questions related to the test? Otherwise, I'm just going to go back to Rankine power cycle problems. Yep.
So we'll have all of the equations, but they'll just not be labeled?
Like what's an example of an equation that would help to be labeled? I'm trying to think of what. So I tend to usually, right, I guess they're, right, they won't be labeled. I mean, like, I'll give you the equation for quality, but it won't say what it is. Yeah. I feel like there might be some that I occasionally label, but I mean, yeah, you should
be able to recognize.
Yeah. All right. Okay, so last time we came up with the following things. We went through this whole long derivation, and I'm going to list sort of the punchline first. This is maybe the most important of all of them, that the efficiency for this power cycle you can calculate as 1 minus the entropy at state 2 minus the entropy at state enthalpy at state 2 minus enthalpy at state 3 divided by enthalpy at state 1 minus state 4. And then on the way to getting, the way we came up with this was, remember, we did the 4 separate first law for control volume calculations. And those are also going to be important for doing these kind of problems. So we also got, so the work produced by the turbine, that rate divided by the mass flow rate is equal to H1 minus H2. The rate of heat transfer out of the working fluid at the condenser divided by the mass flow rate is H2 minus H3. The rate of work that has to be provided to the pump divided by the mass flow rate is equal to H4 minus H3. And this is the one that there's another way to calculate this stuff. So this is also equal to the specific volume times the quantity pressure at state 4 minus pressure at state 3. Anyone remember why it is that we have this second way of calculating this stuff for the pump? This is important. Remember that the pump is the one place where we have a liquid through the whole process. And so we did this with the incompressible assumption. And all this stuff is useful. And then the last one, the rate of heat flow into the working fluid at the boiler divided by the mass flow rate is H1 minus H4. Okay, so our basic goal with any of these problems is going to be to calculate the enthalpy, the specific enthalpy at all four of these states. Once we do that, we can answer just about any question. Okay. And so I'm going to do an example problem. We have an ideal Rankine cycle. That's the only kind of Rankine cycle we've seen so far. And water is the working fluid. You might think in a super high-tech power plant, they'd use some crazy chemical that has thermodynamic processes that they develop. But almost always water is the working fluid. It, has a reasonable saturation range for pressures and temperatures, and it's not poisonous to throw out, and it's abundant, and they need a lot of it.
Do they sometimes add like certain chemicals to the water? I don't know, like salt.
I don't think so. I don't think they do. Yeah, that's a good question. I mean, well, one other thing is like if you add things to the water, it destroys the turbine fans, and that's a concern because you're pumping this working fluid through the turbine at very high pressures. Right. So, okay, saturated vapor enters the turbine at a pressure of 8 megapascals. So that's 8 times 10 to the 6 pascals. And saturated liquid exits the condenser at 0.08 megapascals. The net power of this from this cycle net power output is 100 megawatts. What's the net power? What's a mathematical expression for the net power? Well, it's pretty close to, hopefully it's pretty close to just being the power output at the turbine. But remember, you also have to give up some power at the pump. So this is WT dot minus WP dot. And here's what we want to calculate. We want the efficiency, the back work ratio, the mass flow rate, the rate of heat entering the working fluid at the boiler, so QH dot, and then the rate of heat leaving the working fluid at the condenser. So that's Q sub C dot. And then we're going to talk about one more thing when we're done with these, but let's do these first. I mean, the thing I think to keep in mind with these kind of problems is you can get pretty far into this problem before you even think about what you're trying to calculate. Our goal really is just to find those 4 enthalpies, and that's just always going to be the goal. Okay, so I'm going to set up my 4 things, my 4 states. So we have state 1, state 2, state 3, and state 4. From state 1 to state 2, this is an isentropic turbine. From state 2 to state 3, this is an isobaric condenser. From state 3 to state 4, what's that process? It helps a lot if you remember these. This is an isentropic pump. And then the last one from state 4 all the way back to state 1. Yeah, this is an isobaric boiler, right? Okay, and now one thing that always strikes me about looking at these problems is it looks like it gives us so little information. It looks like it's asking us for a lot more stuff than it's giving us, but this is enough information to do all this. But I'm putting it out in this table form so we can just kind of work our way around like, oh, okay, because we know this, we know this. Because we know this, we also know this. And we can just start filling in this table. So saturated vapor enters the turbine at 8 megapascals. So which state is at the entrance to the turbine?
State 1.
Yep, state 1. And it says that this is a saturated vapor. And if it didn't say saturated vapor, but it said that this is an ideal Rankine cycle, then you would remember that this ideal Rankine cycle always has these properties. This is an ideal Rankine cycle. So this is state 1, state 2, state 3, state 4. And so you can see from the ideal Rankine cycle that state 1 has to be a saturated vapor. And we're given that the pressure here is 8. I'll write it as 8 times 10 to the 6, put everything in SI units. So based on that, do we know anything else at any of these other states? Since we have 2 isobaric processes and 2 isentropic processes, you usually can fill out more than one thing with each bit of information. It's an isobaric process from state 4 to state 1. So we know that at state 4, the pressure is also 8 megapascals. And the phase at state 4 is a compressed liquid. And P4 is equal to 8 times 10 to the 6 pascals. and then it says a saturated liquid exits the condenser at 0.08 megapascals. What's the state exiting the...
That's state 3.
So yeah, state 3 exits the condenser, and that is a saturated liquid. And so P3 is equal to 0.08 times 10 to the 6. It's isobaric, the whole process from state 2 to state 3. State 2 this is a saturated mix. But we know that the pressure is 0.08 times 10 to the 6. Okay.
Pressure and state for all 4 states.
Right. So for the saturated vapor and the saturated liquid, we have enough to look up anything we want. For the other two, we would need to know the quality for state 2, and we need one more property for state 4. So how are we going to get these things? Exactly. So what we can do is we can, let me write this down. So we have all we need to look up properties at states 1 and 3. And then one thing we're going to do pretty often is we can look up the specific entropy at state 1. Then that's the specific entropy at state 2, which isn't really something we want, except that we can use that to calculate the quality. So that's also S2, because that's an isentropic process. So we can use S2 to calculate the quality at state 2. Once we have the quality and we have the pressure, we can look up anything we want at state 2. Okay?
It's the same thing with finding one of the properties at state 4 from state 3.
So for states 4 and 3, now this is the one where you have two different options. You can either use the incompressible stuff or if you have a way to look stuff up, depending on what they give you. In this case, what we're going to do is we have the pressures at these two. And so we can figure out what the specific volume is and just use this expression. Okay, so let's start looking this stuff up. So I guess let me move this down. Give myself some room to fill in this table. Okay, so now we have everything we need to look this stuff up. So at state 1, the website says specific enthalpy is equal to 2758 times 10 to the third. And the specific entropy is equal to 5.7432 times 10 to the third. And so since we know that state 1 and state 2 have the same entropy, we also know that S2 is equal to 5.7432 times 10 to the third. So now that we know S2, to find the quality, we can say S2 is equal to the quality times the specific entropy for the saturated vapor plus 1 minus the quality times the specific entropy for the saturated liquid. You could get both of those from the table, or you can plug in a quality of 0 and a quality of 1 into the website. And so this gives you, let's see. Well, let me write it down here. So 5.7432 times 10 to the third is equal to X times the specific entropy for the saturated vapor, 8.2287 times 10 to the third, plus the quantity 1 minus the quality times the specific entropy for the saturated liquid at this pressure. That is 0.5926 times 10 to the third. And you can use that to calculate the quality, and you get that X is equal to 0.6745. Okay, so what percentage of, at state 2, what percentage of the working fluid is vapor? Yeah, 67.45%. So 32.5 whatever percent is liquid. So now we have that. So now we've calculated that X is 0.6745. Now we have everything we need to look stuff up here. Don't ask me what my color codes mean. So now we can just go to the website and look up the specific enthalpy. We get H2 is equal to 1795 times 10 to the third. State 3, we can look stuff up. So we can just get the enthalpy here. So H3 is equal to 173.88 times 10 to the third. And the last thing we need is the enthalpy at state 4. We don't have a way to get that from the website. because this is a compressed liquid, so we need two properties, and the only property we have is the pressure. But we can use the fact that it's incompressible. So the process from state 3 to state 4 is incompressible. And so we can say we know that H4 minus H3 is equal to V times the quantity P4 minus P3. And so if you rearrange this, you get that H4 is equal to specific volume times the quantity pressure 4 minus pressure 3 plus H3. Well, we have those two pressures. That was like one of the first things we figured out. And we have H3. The only thing we don't know is the specific volume. Well, this is water. So water is very close to incompressible over a big range of temperatures. If you want to just approximate it, be a little sloppier, you get good results still treating this as 0.001, 1 over 1,000. If you want to be a little more accurate about it, how would you come up with a more accurate calculation for the specific volume?
Was it PBRT or is it?
Nope, that's ideal gas. But what you could do is, and this is a liquid, but notice that in state 4, in state 3, we have that it's a saturated liquid. So you can go to the website, put that has a quality of 0, it's a saturated liquid, put the pressure, and it'll tell you what the specific volume is. And then you can use that specific volume for that whole process. And it'll be, well, let's do it. Let's see how close it is. So
Couldn't we use stage 3 and 4 the same specific entropy?
yes, they do. So you could enter in specific.
Yeah.
Well, we don't have the specific entropy here. I guess we could look it up. Yep, you could do that. And then you could use pressure and specific entropy. Yes, you totally could do that.
Professor?
Yep.
So we use the quality equation to find the enthalpy, right? The H2. So are there any sort of properties that we can't just kind of estimate from that?
For state 2?
For the finding it with the quality.
Well, yeah, but the state 2 is the only one where the quality helps us. But once we have the quality and the pressure, we can look up anything we want. Yep.
Just generally though, if we wanted to use it for, well, we use it for entropy. For specific volume or density, would that also be a property?
Yes, except you can only do it for state 2.
Mm-hmm.
But yes, for sure, you can look up anything. Yep.
That's cool.
Yep. Right. So once you know for anything in the saturation range, if you have the quality and one other property, you can look up any other property. Yep. Okay, so we were going to go. So I'm going to look up for a saturated liquid and this low pressure. I'm going to look up what the specific volume is. Okay, so this is water. And this is liquid water, so the quality is 0. And the pressure is, we want international. So kilopascals, that is 0.08 megapascals, so 0.880, I think, kilopascals. And you can see the specific volume. I said, if you want to save a few seconds, you can use it as 0.001 for liquid water. This says, okay, it's not quite that, it's 0.001038. So now we can calculate H4 is equal to 0.001038 times the pressure at state 4, which is 8 times 10 to the 6, minus the pressure at state 3, which is 0.08 times 10 to the 6, plus the specific enthalpy at state 3, 173.88 times 10 to the 3rd. I didn't bring my bag. Can someone calculate that?
Into my calculator.
Thank you. And so I get 182,000 100.96. If you would have used 0.001 as an approximation, you would have gotten 181,872. So this is pretty close. And so then here we calculate this. H4 is equal to 182,100.96. Now we have all 4 of those enthalpies. And until now, we haven't even thought about what we're being asked for. But now that we have those 4 enthalpies, we can go through these questions. So part A, we're trying to calculate the efficiency. We know that this is 1 minus H2 minus H3 over H1 minus H4. So that is 1 minus 1795 times 10 to the 3rd minus 174 times 10 to the 3rd divided by 2758 times 10 to the 3rd minus 182 times 10 to the 3rd, just rounding all this stuff. And you get that the efficiency is 0.371. Part B, it asks us for the rate of power produced, put into the pump divided by the mass flow rate. Nope. It asks us for so what it asks for is the back work ratio here. So this is the back work ratio is the rate of work required by the pump divided by the rate of work produced by the turbine. You want that to be big or small? Small, yep. And so you can rewrite this as WP dot over M dot divided by WT dot over M dot. And then use the stuff in the box here. We can calculate WT dot over M dot, WP dot over M dot. So this is H4 minus H3 divided by H1 minus H2. So that is 182 times 10 to the third minus 174 times 10 to the third divided by 2758 times 10 to the third minus 1795 times 10 to the third. And you get 0.00831. Okay, so what percentage of the power that you're generating by the turbine is spent running the pump?
About less than 1%.
Less than 1%, exactly. 0.8%. Yep. Okay, the next one we want is the mass flow rate. So how are we going to get this? Well, we know that the net power that is the rate of work produced by the turbine minus the rate of work that's spent by the pump. We're given that that is equal to 100 times 10 to the 6. And we know that WT dot over M dot is equal to H1 minus H2, which is 2758 times 10 to the third minus 1795 times 10 to the third. So this is 963 times 10 to the third. And we know that the work input to the pump divided by the mass flow rate is H4 minus H3. And that is 182,000 minus 173,880. I guess this was actually 100, wasn't it? And so this is 8,220. And so you can think of this as WT dot minus WP dot divided by M dot. Um, and then times m dot is equal to 100 times 10 to the 6. No. What? What am I doing? Don't do this. Okay, I'm all right. So this is just rewriting this stuff. So this is equal to 963 times 10 to the third minus 8220. So this is 9,547,80. And now we know that if we multiply this by m, we get this. So m dot. So m dot times 9,547,80 is equal to 100 times 10 to the 6. And so the mass flow rate is 104.74 kilograms per second. And then D, so for D, we're looking for the rate of heat entering the working fluid at the boiler. We know that, I guess I usually call this sub H. So we know that Q dot H over M dot is equal to H1 minus H4. And H1 minus H4 is 2.576 times 10 to the 6. And now we know what M dot is. So QH dot is equal to 104.74 times 2.576 times 10 to the 6. And so you get 2.70 times 10 to the 8 watts. That's joules per second. And then last, we want to figure out the rate of heat leaving the working fluid at the condenser. So this is QC dot. We know that QC dot over M dot is H2 minus H3. And that is 1795 times 10 to the third minus 173.88 times 10 to the third. So that is 1.621 times 10 to the 6. And so the rate of heat transfer out of the working fluid at the condenser is 104.74 times 1.621 times 10 to the 6. And that is 1.70 times 10 to the 8th watts. Okay. This is a pretty standard way that these problems go. The one difference could be that instead of giving you the stuff that you need to use the incompressible assumption from state 3 to state 4, they give you the stuff directly that you need just to use the website to find H3 and H4. But other than that, this thought process always goes the same. And so next time, I guess after the test, I'm going to do a thing on here where we can, show you how to do a thing where you can calculate how much water flow you need through the condenser as a cooling fluid in order to get that amount of heat transfer. And then that's really all there is to this stuff. Okay, that's all.